Log on, tune in, find out. Another good idea from Cambridge.
Okay, so today I'll talk about more about stability conditions on K3 surfaces. So I'll mainly talk about, so now let me recall, so what our setup was in general for a triangulated category to look at the space of stability conditions on this category. So the stability condition consisted of the slicing and the stability function, and implicitly I might be looking only at numerical stability conditions or at stability conditions for which this stability function factors over a fixed portion of the K group. So in particular, this set of stability conditions is contained in the product of the set of slicings of D and K star or gamma star if we fix a quotient of K, so where K star is the set of the linear space of linear maps from K to C. Okay, so in particular I can map down to this linear space. So this we should think of a linear space, for instance, a finite dimensional space, mapping sigma to just the stability function. And then there was this one theorem of Bridgeton saying that the fibers somehow are discrete, namely if I fix the z, then the distance between the 2 points, so this would be two slicings P and Q, is at least 1. And more precisely, he put a topology on this space such that on the connected components, this projection is a local homomorphism onto a linear subspace. Okay, so for all connected components, there exists a linear subspace such that the projection here is a local homomorphism. And so now there are always two questions in order to understand the space of stability conditions. So let's stick to one connected component. What is the image of this map and what are the fibers? So what is the image of pi and what are the fibers? Okay. So now let's look at the case of K3 surfaces. So suppose X is a projective K3 surface, and let us do this over C for simplicity, but that's not, the C is not really needed. An algebraically closed field would be fine. And then we constructed, or I outlined the construction of stability conditions. Namely, I was looking at stability functions of the type given by the exponential of b plus I omega, where b and omega are elements in the Neuron-Surveyor group R, and the heart of the bounded T structure was given as the tilt with respect to torsion theory that I've given explicitly, where there was a beta that in this case where I fix a class B, this was just the intersection number with omega and then omega itself and f. So roughly the torsion part was where slope is bigger than beta and the torsion free where the slope is smaller or equal to beta. Okay? So these gave actually numerical stability conditions on dBx. So the bounded derived category of coherent sheaves on X. And if, so there, I had to make an assumption, namely, well, there was this one thing that directly you can only prove it for rational classes. And I needed the square of omega to be big enough. More precisely, I needed that Z of E is a positive number for all rigid stable bundles. But that was the condition I needed. Okay, so it's not hard to believe that these stability conditions constructed this way actually are contained in the same connected component. Okay, so we shall talk about this connected component. So these are all we fix now connected component and ask these questions. And moreover, for this connected component, the linear space V sigma is actually the whole space. So here n of x is the extended Néron-Severi group. So you can view this as the algebraic part of homology, or write this out explicitly as the degree 0 part, the Néron-Severi group, and the degree 4 part. So these are, this is generated by well, this is the rank, this is the degree, and this is the determinant. Okay. So now I want to answer these questions in this case, and note that so this is a space of dimension, a complex space of dimension rho plus 2. So rho is the Picard number. And the theorem of Bridgeland now says that, so I state the theorem and then I explain everything that comes up in the theorem. So the projection pi from step D to K star induces, so we know the fibers are discrete, and in this case induces a covering map pi from this connected component, this distinguished connected component, to a space which I shall denote P plus 0x. And this is the open subspace of nx star. And with the group of deck transformation isomorphic to out 0 sigma dBx. Okay, so there, I mean, the only thing, so I haven't explained what this P plus 0 is, I haven't explained what this group is, and so on, but this is the statement. I tried not to explain what's written in it. It will take some time. So the this, in a way, answers these two questions, namely, this is a thing that is explicitly described, so we know what the image is. right? This is the first question. And this describes the fibers, right? The group of deck transformation is isomorphic to this one. That means the points, all points in one fiber are transformed into each other by the action of this group. Okay? So in a way that answers these two questions. What remains, I mean, this one there we will see an explicit description. This one we don't have a better understanding than, I mean, the description is not explicit, as explicit as we want. And the idea is a bit, I mean, to motivate even like, if I couldn't convince you that stability conditions are something interesting, that in this example for K3 surfaces, I get something interesting out of that some of the space of stability conditions, or at least this distinguished component, is related to two interesting structures, namely this group and this open subset here, which I'll make a kind of period domain that should indicates that the stability conditions, the space of stability condition is something interesting to study. Okay, so now let me dive into these definitions. And I'll first stick to the image. Okay, so let me describe the image of this map explicitly. So first of all, I identify this linear space, the dual linear space, with just a complexified extended Néron-Severi group using the intersection pairing on the cohomology on the K group. Okay, so Z here corresponds can always be written as the intersection product, so the Mukai pairing with some class omega with complex coefficients. Okay. So then, remark, so here what I use is, of course, that the Mukai pairing is non-degenerate. But we know a bit more, namely we know that the Mukai pairing on the extended Néron-Severi group, so it's certainly a direct sum of the intersection form on the standard Néron-Severi plus the intersection product of degree 0 classes and degree 4 classes. So these two, Z plus Z, they form a hyperbolic plane. And so there's one positive and one negative eigenvalue in the Néron-Severi group by the Hodge index theorem has signature 1 something. So this thing has signature 2 rho, so 2 positive eigenvalues, and all the other ones are negative. If you diagonalize it over R, then you have 1, 1, and minus 1, and all the others are minus 1 on the diagonal. Okay. So, and then define the first thing, P of x. So we slowly approach this P plus 0 of x. P of x, this is just the set of positive, so the set of vectors in this complex vector space such that the real part and the imaginary part, so now real and imaginary part are now vectors in the real vector space and expanded by the algebraic classes. And if this vector space spanned by these two classes is a positive plane in the real vector space. So this is in Nx tensor R. So now this vector space is a real vector space with an intersection form of this signature. So there is enough space for a plane such that the restriction to this plane is positive definite. Okay? And the condition here is I want this plane to be positive definite. Okay? A positive plane. Okay. And now due to the signature, this thing has actually two connected components. Let me put the plus here. Plus two connected components. And this should remind you of the fact that in the Néron-Severi group, due to the Hodge index, theorem, the cone of classes of positive square has two connected components. And this corresponds to these two connected components. And I choose my notation such that the P plus X contains actually the elements x b plus I omega with omega ample. Okay, so let me maybe write this out. What it means, that what is, if I take omega, capital Omega, to be the exponential of b plus I omega, then what is its real and imaginary part? So the real part of omega is, remember, this was 1 plus b plus I omega, just the definition of the exponential, b plus I omega squared over 2. So the real part of it is 1 plus b, so degree 0, degree 2, degree 4, b squared minus omega squared over 2. And its imaginary part is omega plus b intersected omega, degree 2 and degree 4. Okay. And then it's not difficult to see that this is actually a positive plane. For instance, if you put b equals 0, then you see it's 1 minus omega squared over 2. This has positive square. And similarly here, omega squared for an ample class is positive. So that's the positive plane, because these two classes are also orthogonal to each other. And as long as you stay with your ample class, I mean with the class omega in the ample cone, so in one connected component of the positive cone, that will stay in the same connected component. Okay, so this is the p plus x. I mean the whole description of this p plus 0x is quite involved, but we'll see that we end up with something that is studied in other areas and actually well known. Okay, questions so far? Okay, so next I need as a notation the set of minus 2 classes. So delta is the set of minus 2 classes in this lattice. So these are integral cohomology classes. So these are the roots in the lattice. And why am I looking at these things? Well, we actually know a few objects whose Mucha vector is this class. So let me give you a few examples. So for instance, if you have a smooth rational curve in X, then the Mucha vector, so which I defined yesterday, of the structure sheaf OC, so OC is a sheaf, a torsion sheaf on X, I can twist it by K, and this has this Mucha vector, K plus 1. And you see if you take the square of this one, this only squares with the degree 0 part, which is 0. So the square of this one will be the square of this class. And in the P1, I mean a smooth rational curve is a minus 2 class on a K3 surface. Another example is you can take any line bundle on peak X. Then its Mucha vector is of this form. It's 1, then the first Chern class of L, and then its first Chern class squared over 2 plus 1. And this again, if you compute it, is a root. Okay. And last but not least, those have come up already. I mentioned them again there. So if E is a mu stable rigid bundle, so rigid means x1 EE is 0, then its Mucha vector, so this was rank C1 and Chern 2 plus rank is again a root in this thing. Okay. So and now I take out all classes. So I take this P plus X, and from there I remove all classes that are orthogonal to any of these minus 2 classes. So, so now I put P plus 0x right? And being orthogonal to a minus 2 class for a class capital omega means its real part is orthogonal to it and its imaginary part. So if you want, there are actually two conditions. So this set usually the set of roots is infinite. So you start with a nice open subset in a complex vector space, this P plus X, and then you take out an infinite number of hyperplanes namely these complements to delta, but you can prove that this is always locally finite. So there are infinitely many things you take out, but locally it's only finitely many. So now this is a description, and the first part in this theorem says the image of this component here is this set. Okay. Already you see, I mean, it's an interesting thing. It's the complement of a hyperplane arrangement in some way, so that shows that this component, the sigma or the space of stability condition in general, is so interesting. Why these -2 classes, these roots come up? Well, this will become clearer at several later, but you already see here that when I wanted to construct these stability conditions, there was a condition that, for instance, the z of E cannot be 0, and that those classes exactly are taken out there. I'll come to this. So I want to separate these two things, the image and then speaking about the autoequivalences. Okay, so now I mean, the description is straightforward, but it's not something that should I say? I mean, something very similar occurs in many other branches, namely in the modular space theory of K3 surfaces, but not quite in this form. So I try to rephrase this, or describe this space differently in terms of period domains. So in particular, I should just make this as a comment. I mean, this is a complex manifold, this P plus 0x, but it's never a quasi-projective variety. Okay. So now instead, I look at something that is more familiar, namely I look at a period domain D inside the projective space associated to this complex vector space of dimension rho plus 2. So this is the standard period domain of all points, of all lines, represented by some vector x, or yeah, why not x, such that its square, I still have the Mukai pairing on this thing, this square is 0, and cut with its own conjugate is positive. So this is an open subset, real open subset of a quadric, of a smooth quadric. So open subset of quadric. Instead. So again, this has two connected components, which I write as d plus d minus. And I can describe this differently as the space of oriented positive planes in the real vector space associated to R. So this is the Grassmannian of all planes it's a positive plane, and in addition I fix an orientation. So this positive is the 2 is a plane, the P is for positive, and this O is that in addition I fix an orientation. So this is a standard argument mapping, taking an x, so line, represented by class, taking real taking real and imaginary part to span a plane in here. And then this is related to this P of x there. I can namely take P of x and map it. Say it again? No, I still mean this still has two connected components if you want, because I can change the orientation. Right. So the P of x maps to D just by taking an element omega and map it to the class omega. And this is not an isomorphism because obviously if I only fix the class in the complex vector space, then I have a choice to write, for the real and imaginary part. So this is a GL2 R bundle, but since I also fixed the orientation, this is actually a GL2 R plus bundle. And of course, I can choose the notation such that P plus x under this goes to D plus. at some point I want to say this. Okay. And similarly, I can define d plus 0 as the complement of all these hyperplanes. So the hyperplane in this language would be a Heegner divisor. Take those out. And now the advantage of working with this d instead of this p of x, the d still is just the complex manifold. It's not a quasi-projective variety. But if I now take like a finite index subgroup of the orthogonal group of nx, so an arithmetic group, finite index, then Bailey-Burrell tells us that d0 plus divided by gamma, and which is an open subset of d plus divided by gamma, are both quasi-projective varieties. And so they usually come up as moduli spaces of lattice polarized K3 surfaces. And have been studied for a very long time. Okay, so then you can start asking questions about natural compactifications, modular description of compactifications, and so on. Okay, I'll get back to this quotient, but let me explain why the occurrence of this GL2 plus R is quite natural. I mean, this construction is linear algebra, so there is a GL2 plus R, but actually this GL2 plus R can also be seen in the language of the stability conditions. Namely, so if I write my diagram, so this is now general again, nothing to do with K3. If I have the space of stability conditions and I map it to K star, then on K star I have this action of GL2 R by mapping. So this is a linear map from K to C, and if I pick a matrix, a 2 by 2 matrix, I can just compose, and I view the C as R2, then I can just compose the stability function with a matrix. Okay, and I get again a linear function, so I would map this to M, and to get a right action I would take M to the inverse composed with that. Okay, so that does not quite lift to an action on the space of stability conditions, because, for instance, the matrix -1 corresponds to rotation by pi. So this will be this one. And on the other hand, so this is a matrix -1, -1. And on the other hand, we know that the shift also acts like this. And if I do this rotation twice, then in GL2 I get the identity, but on the level of the derived category I get twice the shift, which is clearly not the identity. And this is the reason why I have to lift this action to, I mean, I cannot let this act on the space, but I can let it act as universal cover. So this is a Z covering, and this one then acts on the space of stability conditions. And so, in a way, passing from P of X to this period domain D, this corresponds to passing from stub to the quotient of stub by the GL2R action. And the GL2R action essentially just keeps the slicing of the triangulated category, but forgetting about the actual faces. It's just like a semi-stable object remains semi-stable, but I forget about the facing, but I keep the ordering of the faces. This is roughly what the GL2R action does on the space of stability conditions. Okay, so so this was one attempt to talk about this image. Let me, to give you a better idea what this image looks like, let me look at those stability functions we have studied. Namely, let's look at this the set of exponentials b plus I omega, which are in this p plus 0x. Okay, so how does this look like? Well, it's still difficult to draw because I have two classes, namely this omega and this b. So let me fix the b and then try to draw a picture for the omega. So, okay. So what do we know? We know by construction that actually every class omega that is ample was allowed as long as its square was big enough. So let me draw the positive cone, which was somewhere there, a bit bigger, maybe even bigger. So this is the positive cone. In the Néron-Severi group R. So here are all the classes omega, all the ample classes, but possibly more. So first of all, let me recall how to describe the ample cone itself. Well, to describe the ample cone, you take out some hyperplanes. So for instance, like this. And each of these hyperplanes here is given by a -2 curve, so a smooth rational curve in X. And all the classes that are orthogonal to it, that gives you a chamber structure of the positive cone. And one of the chambers, for instance this one here, will be the ample cone. So that's a theorem for K3 surface. The class on the K3 surface is ample if it's in the positive cone and positive on all smooth rational curves. So if there's no smooth rational curve, then in fact it's the whole ample cone. Usually you would draw a picture like this. That's not quite true what really happens in general, because usually you would have an infinite number of rational curves. And in fact, there are theorems to say that there are so many rational curves that this round part does not really occur. But anyway, so that is this is what this theorem you probably all know really says. So this theorem that I have to take an ample class was that it's positive on all the curves. So if you go back to the proof, that was really in the proof that I needed to deal with the torsion sheaves in dimension 1, that I needed this class omega to be positive on the curves. So that describes this one. But then there was this other condition. Either I choose the omega square big enough, but that was like a very strong assumption, or the finer one was that I make sure that the spherical objects, so these rigid stable objects, are not mapped to a positive real number under the stability function. So in particular, I have to take out. Let me try to draw this. So maybe I should say this is like one of these delta perp. So these are these hyperplanes I have to take out, right? But there are others. So these are the ones corresponding to smooth rational curves. But there are others like this one, where here in this case delta is V of a rigid stable bundle, and then this condition that the stability function has to be positive and has to be negative is a condition that this thing is not a standard stability condition. So this class here I have to take out. That won't be in the image by my description. And then this ray here, this half ray here, is in the image, but it's not one of the standard stability conditions we constructed. And these things, there might be many of those. So everything else inside here we have actually constructed, have realized explicitly by these standard stability conditions on the derived category. I hope this gives some feeling for this space. Okay, now Okay, so let's suppose we understand now what the image is. Now I turn to the to the fibers. So this theorem is still there. I have to describe this. Thing. So if I have an autoequivalence of the derived category, it always induces an induced action on the cohomology. That's true for any variety, at least if you take rational coefficients, but for K3 surface, it is actually an automorphism of the integral cohomology, not preserving the degree, but it preserves the Mukai pairing and the Hodge structure. But for the moment, that's not so important. So there is an action, there's a representation of this group into the orthogonal group of the full cohomology. And if I put the 0, that means I want to take those that act as the identity on cohomology. So that's the kernel of this representation. And in there, I can also look. So whenever I have an autoequivalence of a triangulated category, I can apply to stability condition, just transfer all the structure that is given by stability condition to the other side via this autoequivalence, and that will again be a stability condition. And there's no reason why this distinguished component Bridgen has constructed is actually preserved under this group. So he has to fix, so he has to add this condition, which might be void in the end. We simply don't know. So in addition, so phi h is the identity, and we want that a stability condition in this component is again stability condition in this component. So I'll mention this later, but presumably this should be inequality. Okay, so for later use, let me mention there's also a slightly bigger group than this one, namely the group of all equivalences for which not the action on the full cohomology is the identity, but only the action on the transcendental part. That's slightly bigger. It's a finite index subgroup in there. Okay. So this is the group. That's the definition of the group in this theorem. So for those who have never thought about equivalences, derived equivalences, in particular of K3 surface, let me give you a few examples of equivalences that we know exist. So the easy ones are, I take any automorphism of X itself and just let it act by F lower star or F upper star on the derived category. Those are still there. Then similarly, classically, any line bundle, I can let it act by tensor product on the derived category, and this is again an equivalence. And then more complicated ones are the spherical twist, the Seidel-Thomas twist. So whenever you have a spherical object, that means its X algebra has the algebra of a two-dimensional sphere. Then there is an autoequivalence which is called the spherical twist. Which maps any complex to the cone of the evaluation map from morphisms from E to F and then to F. This is E and this is F. And I want this in all degrees, so I also want extensions. And the fact that this is an equivalence is actually very easy. So there's a very easy argument, namely showing that the first step is TE is fully faithful by using a general criterion on the spanning class. And the spanning class consists of the object E and everything that's orthogonal to E. It's actually not so clear whether there is anything orthogonal to E, but still this is a spanning class. And on those, you can easily compute that the spherical twist of E is a shift, in this case by 1, I believe. And for anything orthogonal to F to E, this is just F. And clearly this is fully faithful. And then since we are both sides have the same dimension and trivial canonical bundle, this proves that this is an equivalent. So these are the usual criteria of Bonn, Orlov, and Bridgeland. So omega x trivial then implies TE is an equivalence. So I have these spherical twists, and we actually know what they do on the cohomology. And they actually fit nicely into the classical picture of -2 classes describing this ample cone I'm about to erase. So the action of the spherical twist on cohomology is the reflection in the hyperplane orthogonal to the Mucha vector of the spherical object. Okay. And in particular, you see if you take the square of a spherical twist, its action on cohomology will be the square of a reflection, so it will be the identity, and hence all these things here will be in the kernel of the cohomology representation, so they will be in here. And now, I mean, from the very simple picture of the ample cone I've drawn, you see there might be many smooth rational curves, so there are many -2 classes. There are even more -2 classes if you allow spherical bundles, so somehow stable, rigid bundles. And if you allow even complexes, then you get even more spherical objects. So all these spherical objects, their squares will be elements in this group. And the big question is how we can actually describe this group. So so maybe I should put this down explicitly. So two open questions are whether this is actually the only component, and whether if it's not, whether it is at least preserved under all equivalences. That would be enough for most of the purposes. Then I would just not think about the other components. But we don't know this. There's only one result, namely that, I mean, I have this action of the autoequivalence on this set, and I have the natural action on this set, and at least I know that this set is preserved. A priori, something in here under an autoequivalence might be mapped to the other component, to the p minus, but this does not happen. It's a result we proved some years ago. So at least out dbx preserves this connected component of p of x. I mean, this looks like a rather technical statement. In fact, the proof is very technical. If you want to dress it up, then you can say this is predicted by mirror symmetry. But this is of no importance here. What Bridgeland's proof of this theorem shows, actually, the proof of the theorem shows that there exists a natural map from the fundamental group of this p plus 0 x to the outer equivalences of dbx, and in fact of those acting trivially on cohomology, because this is, I mean, if I have a covering, then there's and I look at the action of the fundamental group of the space I'm covering, then they preserve the fibers, right? So this sigma here by this theorem will be a quotient of the universal cover of this thing. So the fundamental group acts on the fibers, and so has to act trivially on the cohomology, and this is this map. But having already this map and constructing a map like this, I mean, a group homomorphism, this is highly non-trivial, and this is part of the proof. And in some sense, he shows that the image is this space. Where did I put the sigma? I forgot. Up there. Okay, but note that's a nice description of this group as a quotient of a fundamental group. But note that this group here is not even finitely generated. Well, in general. Okay, so now this is what we know, and now I come to what we don't know. And this is a conjecture of Bridgeland. So I give the weaker version first, and then the other strong one. So first part would be sigma is simply connected. And if you're courageous enough, you could actually try to answer this first question, whether this is this the only component, or the second one that at least preserved by the group of outer equivalences. And in terms of this map here, this means the first one means if this is simply connected, that means this is the universal cover of this complicated space p plus 0. So this corresponds to saying that this group homomorphism constructed by Bridgeland is injective into the group of outer equivalences. And if sigma is preserved by it, then this corresponds to the statement that this one is onto the group of outer equivalences that act trivially on the cohomology. So then the second condition here would be void, and these two groups would coincide. So eventually, what we would like to have is eventually the conjecture is that the group of outer equivalences acting non-trivially on cohomology, this is the part I don't know how to describe, is actually isomorphic to the fundamental group of something complicated. So in particular, note that in this picture here of stub sitting over K star, in the case of K3 surfaces and this particular component, the fibers are huge. They correspond to a group which is not finitely generated. Okay? So it's not that for each stability condition, for each stability function, I only have the shifts of the stability condition, but much more. Okay? Okay, so let me rephrase this, because this is always be a little frightening, this non-finitely generated group. So this can be rephrased as follows. I can, instead of looking at the fundamental group of this complex manifold, which is so complicated, I can look at this quasi-projective variety and say that the conjecture is that the group of autoequivalences, the full group of autoequivalences, is described as the fundamental group of a quasi-projective variety, namely this thing d plus 0 divided by some group gamma, where gamma, I didn't specify before, this was an arithmetic group. It's still up there. It's a finite index subgroup, and now I actually give you this group. This is the subgroup of all Hodge isometries of the full cohomology. So that preserves this one preserves the intersection form and the Hodge structure, and there's an issue about the orientation, and moreover acts trivially on the transcendental part. So this identity on the transcendental part. This is a finite index subgroup of O of this thing, and this is now the fundamental group of a quasi-projective variety. And in particular, this would confirm a conjecture by, I made one mistake, but I'll correct this in a second. This would confirm a conjecture by Kontsevich, roughly stating that out dB for Calabi-Yau manifold should always be the pi1 of some quasi-projective variety. And in particular, the pi1 of a quasi-projective variety is always finitely generated. So I've to make one comment and one correction. That's not quite true. I only described the group of autoequivalences modulo the double shift. But this group is easy to understand. I mean, this is just Z. I have to divide out by the Z because that's not that corresponds to the fundamental group of GL2R. So this is essentially this Z here. I have to divide out. And now there's this strange thing that from the very beginning I wanted to describe this group. This is the group I'm really interested in. I want to describe whenever you have a triangulated category, can you so you want to first you want to see what are the other varieties that give the same triangulated or derived category, and then the next step is, once you understand this, what is the group of autoequivalences of this group of this category, and this is the thing I want to describe. Then I said, well, I can't quite do this. Let me try to describe this subgroup, and then this subgroup conjecturally is isomorphic to group, fundamental group, but otherwise horribly, namely not even finitely generated. And then I went back to the full group, and this group somehow behaves much nicer. This is a finitely generated group, namely it's the pi1 of a quasi-projective variety. Okay? And that means it's a finitely generated group, but it's what's called non-residually finite, so it has non-finitely generated subgroups. Okay, so you have to live with it. And then there's a second correction I have to make, namely when I do this quotient here, I have to view this as a Deligne-Mumford stake. So actually, I take the orbifold fundamental group of this one, which is still finitely generated. So that's right. Okay. We've seen the last point I want to make concerns these -2 classes or spherical objects. So we've seen these -2 classes and spherical objects coming up at several points. For instance, in the construction of stability conditions, there was this condition omega squared at least 2, or z of e being a positive real numbers for spherical objects. That was the first time they came up. They come up again in the description of this p plus 0x, because I have to take out everything that's orthogonal to minus 2 classes. They're coming up again in the examples when one tries to write down interesting outer equivalences. These are the ones that besides maybe the automorphism group of X, are the most interesting ones. And I want to conclude with something where the spherical objects come up again, but more directly related to stability conditions. Of course, all these aspects are related. It's not describe completely different things. So you might now wonder what is this set of spherical objects. So if I define S to be the set of spherical objects in dBx, so this is just a subset of the category of the set of objects in dBx. And this dBx contains like bundles, sheaves, and so on. Usually they come in moduli, like point sheaves, the points vary in the surface. Then there's a moduli space of stable bundles in it of high dimensions, and so these are some of the rigid objects. These objects are discrete in the set of objects. Okay, so this is a discrete subset. So this is this condition here that the x1, which would be by this definition h1 of S2, and S2 is of course simply connect, so that would be 0. And so this is a discrete subset. It doesn't seem to know very much about the surface because it's just a discrete set. But in fact, what you can prove is the following: if I take two stability conditions, so stability condition given by a slicing and a stability function, and then another one, W in stability conditions on the surface X, and I have to assume that they are actually in this distinguished component, which presumably is the only one there is. Then sigma equals tau if and only if, for instance, the slicings, well, first of all, this is a condition I have to put, Z equals Q. And that's easy. So I'm in a fiber of my map, of my period map, and so I'm in the fiber of this map here. And then the remaining condition is on the slicings. So of course, two slicings coincide if this P of phi equals Q of phi. But the theorem says there's actually enough to test this on the spherical objects. So for all phi in the real numbers, the semi-stable objects of phase phi, which are also spherical, coincide with the semi-stable objects with respect to Q, which are also spherical. And this then allows to write down an equivalent metric. So there exists a metric, an equivalent metric on the space of stability conditions to the one I described before. Actually, I should say on this distinguished component, which I can write like d of sigma and tau. Let me write this ds, so like the spherical metric. This is the maximum. First of all, I want, of course, measure the difference between the linear functions. I'm sorry, this is not q. This is, I'm sorry, this doesn't make any sense. W, z minus w. And the second condition is, I remember when I introduced the metric on the space of slicings, there was this supremum over all objects in the category. And then there was this objection, how can I ever compute this? And here there's again a supremum I have to take, but this time only over this discrete set of spherical objects. This is the sup of phi plus minus of E with respect to the first slicing, so that would be P, and phi plus minus with respect to Q. It's still a big, it's still a big set, but it's discrete, and I don't have to take I don't have to test all vector bundles of parameterized by some moduli space. Okay, and I think this is a good place to stop. We have seen the spherical objects coming up everywhere. They are supposed to encode somehow all the information, but how to actually pack the information from which side we have to go to the other, that's not so clear. Okay.